Hello everyone, I'm Ravi Kumar Singh from TCS Research India. Today I will be talking about our work in which we propose PAEF framework to identify performance anti-patterns and accelerate the model training. Let's talk about the motivation behind developing PAEF framework. So, an MLDL pipeline spends most of the time in data preparation as shown in this figure. There are several steps of data preparation in MLDL pipeline starting from source specific to training specific data processing. Now, the training specific data preparation consists of task and model specific components. So during training, the training specific data preparation can be a major bottleneck which sometimes developer ignores. We will explain this with an example in the next slide. Let's discuss the training specific data preparation effect on model training in this slide. So in model 1, the data preparation takes up to 17% of total training time. However, in model 2, which is more complex recommendation model, takes up to 87% of the total training time, leading to performance anti-patterns. To address this issue, we have introduced PAEF framework to provide a solution that manages the data movement and transformation between CPU and GPU during model training. Now moving to the PAEF architecture, PAEF is a framework that takes MLDL pipeline and its dataset as an input and automatically accelerates the fed MLDL model training by removing the data preparation performance anti-patterns. It has basically three components: static analyzer, dynamic analyzer, and accelerated code generator. The dynamic analyzer employs scaling and NV profilers to identify bottlenecks associated with compute time and memory transfer time. In MLDL training pipeline, this module helps user to recommend top K lines which are degrading the performance. The static analyzer consists of two sub-modules named metadata module and anti-pattern finder module. This metadata module holds the meta information about objects, function used in the model training and save this metadata into files. This metadata is fed to the anti-pattern finder module, which identifying the various performance anti-patterns within the MLDL pipeline. Now the code accelerator module uses the output from static analyzer to find and address the performance anti-patterns in the MLDL training pipeline. It creates optimized code through two methods. In one method, it generates the optimized code automatically, while for other method, it gives solution description with some hints and suggestions, and the user writes those optimized code based on this direction. PAEF framework is also configurable to more performance anti-patterns. There are 6 anti-patterns, but I will be discussing only 2. Please refer to our paper for more info. First one is CPU operation function. This flowchart shows performance anti-pattern and its solution. When training a model on GPU, certain functions can slow down the process and prevent the GPU from being fully utilized and resulted in increased CPU-GPU communication overhead, which, which eventually degrade the performance of the model training. Such function may be running on the CPU only. We come up with a solution in which we execute all the functions with CPU operation before the training so that GPU can be fully utilized during training. However, it is not always to apply this kind of optimization in model training. It is only possible when function data is independent of the model training. Anti-pattern is a dict isolate. While using dictionary in the Python code during data preprocessing and model training, if the dictionary values corresponding to every key are of list type, we know from the experiments that accessing list can be slow. This was well observed during experiments in both CPU and GPU. Now talking about the solution, the key is to change the Python list to a tensor type as a value in the dictionary before the training at the time of data preparation. It is because accessing tensor is extremely fast compared to the Python list. Now moving to the results which we got using PAEF. So first table shows that how much speed up we got in CPU and GPU by providing solution to the performance anti-patterns using PAEF. For some anti-patterns, the magnitude of speed up is in the order of thousands, while the second table shows the training time and the speed up we got in two industrial recommendation model training. These three recommendation models are NICER and BCD for REC. We have also demonstrated the generalizability of our approach by showing that this tool can be applied to other models. We believe that PAEF can help data scientists and developers to build efficient and optimized training pipeline which leads to faster and more accurate MLDL models.